In this class, we're going to talk about sigma and pi covalent bonding. Now, I know a lot of you will be panicking about this one because it is quite difficult to visualize this, but I'm going to give you 2 tips. And if you can do these 2 things, you'll be sorted for your exam. We don't care about anything else. So the 2 things that you have to be able to do, and they're so simple. Number 1, you need to be able to give me 3 differences between sigma and pi bonding. So if you can give me just 3 differences, you can have 6 marks. Technically, we need 2 differences, but I want you to have a 3rd one in the bag. In case the examiner gives you a particular difference on the exam paper and then they ask you for 2 more. So I want 3, one of them is our kind of our cushion or buffer. So 3 differences between sigma and pi. Now we're going to go through those in a little bit. And actually, if you can kind of understand how sigma and pi bonding form, that's actually going to give you a heap of your differences. And the second thing that you have to be able to do is when you look at a molecule, you have to be able to count the sigma and pi bonds in a molecule. Now to do that, you need to know if you have a single, double or triple bond, how many sigma and pi bonds are in each of those 3. Now, if you can do those 2, you're grand. We're not going to ask you to draw something mad and weird here. So you just need to be able to do that. Now, this next section that I'm going to go through, I'm going to show you how sigma and pi covalent bonds form and what it would look like in terms of orbital overlap. However, you're not going to have to draw it. You don't have to be able to visualize it. And if you can do those 2 things, that's it. That's all you need. So, in our notes, right, when we were doing covalent bonds, and I was showing you how to draw the dot and cross diagram, we used the Bohr structures, where you have your electrons in these orbits, and then we're overlapping atoms and sharing electrons between 2 atoms, more or less. So with this, your diagram would end up looking like oxygen. You have 1, 2, 3, 4, 5, 6. 1 electron to hydrogen and 1 electron to that hydrogen. So there's a molecule of water. Now, when we did atomic theory, we started off with Bohr theory first and Bohr's theory of the atom, and then we moved on and showed the limitations to Bohr's theory, where electrons do not occupy these orbits around the nucleus. They actually occupy orbitals instead. Now, that's a key word. An orbital is a region of space where there is a high probability of finding an electron. That's the definition. But how an orbital is different to an orbit is it's 3D space and your electron is moving anywhere inside that orbital. It's not just stuck to the outside of it. Now, when you actually form a bond between 2 atoms, because your electrons are actually in orbitals themselves, not orbits, there has to be some sort of interaction between orbitals in order to form a bond. Now, it doesn't matter what type of bond you form in terms of covalent bonds. All a covalent bond is 1 orbital is overlapping with another one. That's all the bond is. And when your orbitals overlap, you're sharing electrons inside that overlap space between the 2 atoms. And that's all a covalent bond is. Now, there's 2 types of covalent bonds that we need to be able to describe. They're called sigma and pi. And how the orbitals overlap will actually tell you which of those 2 bonds is actually formed. Now, the next one. There's 2 different ways that orbitals can overlap. Sideways or head-on. But when we did orbitals, when we did atomic structure, you had to be able to draw s and p orbitals. S orbitals are spherical, so they look like a sphere, and p orbitals are dumbbell shaped. In a p sublevel, you have 3 p orbitals, the px, the py, and the pz orbital. Now, I'm only showing one of them here. This is technically the px because it should be along the x-axis. Right, now looking at those 2 orbitals, there's going to be different ways that they can interact with each other. And when your electron is in an s orbital, it's moving anywhere around that s orbital. So this would have to overlap with another one. Now, what can be difficult to get your head around here is how you visualize the orbitals. Now, I said it when we did atomic theory, orbitals do not have an edge. So it's not like the electron is in here and suddenly it bangs off the edge and comes back in. It doesn't. Orbitals don't have edges. It's just space. So inside this space here, you have your electron moving. So when this orbital overlaps with another orbital, it's just two spaces overlapping, which absolutely can happen. It's not like they're merging together, like you're trying to visualize two bubbles merging together. That's not particularly useful because bubbles have edges. So that's actually where I find the fifth years particularly struggle with this in terms of visualizing it. Now, top tip, you don't have to be able to visualize it. You just need to know how they overlap, and that's it. Be able to describe in terms of 3D space how they overlap. Okay? Right. Now, in terms of overlapping, we're going to start with the s orbitals first and a sigma bond. Now, the Greek letter sigma, the lowercase sigma symbol, it looks like this. It's an O with a little kick off of it like that. Now, I am desperate at drawing Greek symbols. Your examiner is not going to be looking at this going, oh my God, that's not a perfect sigma. I don't care. It looks like that. It's fine. It's like an O with a little line off it. That's my sigma. Now, in order for you to form a sigma bond, your atomic orbitals, that's specific that you specify atomic orbitals, overlap head on. And when they do that, they form what we call a molecular orbital. Because when two atomic orbitals overlap, you are forming a bond between two atoms, therefore you are forming a molecule. Now, I'm going to do this in relation to a molecule of hydrogen first. Now, hydrogen has the symbol H2. Actually, it'd be easier if I did it down the bottom, just so then I can put pi beside it. Apologies. So hydrogen has the formula H2. In order for you to draw a molecule of hydrogen, hydrogen has one electron in its outer energy level. So if I was drawing the dot and cross diagram of hydrogen, it would look something like this. There's one hydrogen atom with its one electron. Here's another hydrogen atom with its one electron. And you have a sharing between the two atoms like that. Now, we know that Bohr diagrams are not accurate. So if I was to actually represent that as the orbitals overlapping, think about hydrogen. If I was writing in the electron configuration for hydrogen, one hydrogen atom, it would be 1s1. So your electron is in the 1s orbital in the 1s sublevel. So our outer bonding electron can be found in an s orbital. So if I draw that instead like this, actually, where I draw the spherical orbital for my hydrogen. Now, it's going to look like I'm drawing the Bohr diagram here. I'm not. Imagine that as a sphere. I just can't draw spheres. And your electron is somewhere inside this orbital. So I'm going to draw it there. Now, in order for that to form a bond with another, that actually looks like a positive, apologies. In order for that to form a bond with another atom of hydrogen, a second atom of hydrogen has to be close by. So I also have a second atom of hydrogen where its outer electron is moving around a 1s orbital like that. Now to form the bond, they look like two different sizes, use your imagination. The two of them overlap physically in space. Now when a sphere, that's going to move in and the two of them overlap like that. Then inside this shared space here, you have your electrons and you're sharing your electrons between two atoms of hydrogen. Now those two atoms are stable. In the first energy level, you can fit a maximum of 2 electrons, so they're fine. And that is what we call a sigma bond. It's the head on one orbital overlaps the head on another one. Now before we all lose our minds about this, an An s orbital is spherical. So when you look at a football, don't look at the pattern. It's the same the whole way around. So whether you're looking at the sphere up here, here, on the side, on the bottom, on the back, diagonally, it doesn't matter. It's the same all over. So no matter what way an s orbital overlaps, it will always overlap head on. It can't overlap sideways because it's the head in all directions. So s orbitals will always, always, always overlap head on only. Now, if I was showing the head on overlap of p orbitals instead. Now, p orbitals are this lovely dumbbell shape. Now, they very clearly have different sections and they can overlap head on and side on, which we'll see in a minute. Now, to show this, we're going to form a bond between two carbon atoms. So my carbon atoms, if I put one here and one here. Now, I know carbon has a valency of 4, so it should form 4 bonds. So I'm just going to leave it like that. We can imagine there's 3 hydrogens on each carbon. We're just going to ignore that. I'm just talking about this bond here between the 2 carbons. Now, to form this bond, we need to overlap the orbitals. But think about carbon. Carbon has 6 electrons and its bonding electrons are in p orbitals in the p sublevel. If you write out the electron configuration, it's 1s2, 2s2, 2p2. Now, your bonding electrons are in our p orbitals. So if I was to draw that here, you start off with one carbon atom with its p orbital like that, and you have a second carbon atom over here. It will have one electron in that p orbital and one electron in that one. To form a sigma bond or a covalent bond between these two carbon atoms, the head on this orbital, so this part here, the rounded bit, has to overlap with the head on another one. So they will actually overlap head on. And when they do, you form a bond that looks like this. And that is a sigma bond between the two carbons. And technically those 2 electrons are anywhere inside this bit here. This will form the molecular orbital here when the 2 of them overlap. And your 2 electrons can move about inside that space anywhere between the 2. They're not just stuck in this bit here. They can actually move throughout because you're overlapping 2 regions of space and they don't have an edge. So they can be anywhere between the 2 atoms. Now, that is my sigma bond, showing it for an s and a p orbital. Now, can s and p orbitals themselves overlap? Absolutely, they absolutely can. And that would be if you were forming a carbon bonded to a hydrogen. So the bonding electrons for the carbon are in a p orbital. So we draw it like that. Your bonding electrons in hydrogen are in an s orbital, which is spherical. Draw our electron there somewhere and my electron here somewhere. To form a bond between carbon and hydrogen, this orbital has to overlap with this one. They absolutely can overlap. Now, in terms of what type of a bond that is, it is still head-on overlap. S orbitals cannot do any other type of overlap. They will always be head-on. So when they form a bond, and then inside the molecular orbital between the 2, it would actually merge more together, but I'm not redrawing it. It will look a bit like that. Now, that is also a sigma bond. Now, before we go any further, a couple of bits to recap. Your atomic orbitals overlap head-on. That's number 1. Number 2, s orbitals can only overlap head-on, but p orbitals can overlap head-on and side-on. So that's important. Now, let's talk about a sigma bond. Sigma bonds, when you're forming bonds between 2 molecules, the sigma bond has to form first. The head-on overlap between 2 orbitals is always easier. So it's always going to form faster and it will always form first. Now, a pi bond, pi has this symbol here. And it's the dodgiest pi symbol in the world. But anyway, we're going to go with it. Now, it's like an 11 with a little bridge on the top. Okay, now for pi, this is formed by the sideways overlap of atomic orbitals. sideways or side on. Now, if I was to ask you what orbitals can't overlap side on, S, they can't. It will always be head on. But even though we only talk about S and P orbitals and being able to draw them at leave and cert level, you technically have 4 different types: S, P, D, and F, even though we only focus on 2. So in terms of what can form a pi bond, not S, but the other 3 can. So P, D, and F orbitals can all do this. Now, to visualize this, it is a little bit tricky. So we're going to show it as a carbon double bonded to a carbon. If I was to draw a carbon here, and I draw a double bond between 2 carbon atoms like that, that double bond is made up of 2 different types of bonds. The first one is a sigma. So when you form that first bond between the 2 carbons, it will always, 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 always be sigma. So this carbon atom overlaps with this one. So head-on overlap. It has to be head-on because it's 2 carbons bonding together and your bonding electrons are in p orbitals. So there's my first one, that's the sigma. The second bond that you have here is the pi bond, and that happens when you have sideways overlap. Now remember, when you have p orbitals in a p sublevel, there are 3 of them. That's technically showing px overlap. So 2 px orbitals overlapping together. But there's 2 other ones that could potentially overlap as well. So up here, pointing vertically, that would be the py on that carbon, and that's the py on the other carbon. Now, it's difficult to show it on diagrams like this because I would need to draw giant diagrams to really show this. These orbitals that I've represented here are actually much bigger. So they do actually, once your sigma bond between your 2 carbons forms like that, the other orbitals that are kind of flapping about in space on the top and the bottom, they have to align themselves perfectly. So they have to become perfectly aligned like this before they can actually overlap sideways. And when that happens, that's when you form the pi bond. Now the pi bond will always form second because it takes a little bit of time for your vertical or your Z orbitals to be in the right orientation to be overlapped sideways. So here, even though they look like they're a million miles apart, they aren't. They're actually beside each other and they will overlap. So a lot of textbooks will show this as a dotted line from one sideways overlap like that, and it will also overlap here like this. Now, if I was to draw it a little bit more simply than that, it would be, there's one py, and there's another one overlapping like that. And that's showing the p orbital overlap for a pi bond. Now, there's a couple of key differences between the types of overlap. In order for you to form a pi bond, they have to overlap sideways. With p orbitals, they can only overlap sideways in one way, literally sideways like that. If it's the top on the orbital there, that will be head-on overlap. But it's not, it's the side of one overlapping with the side of the other. Another key difference between them is when you form one pi bond, there's actually 2 overlaps between the orbitals. So when you have 2 p orbitals overlapping, you overlap here and you overlap here. So there's 2 points of overlap, 2 areas of overlap. Now, this is where students get confused because they see a diagram like this, and to the untrained eye, that will actually look like 3 bonds, but it's not, it's 2. You have your sigma bond here, and then you have one pi bond. One pi bond has 2 overlaps, one on the top and one on the bottom. If I was then to form a triple bond, which is another type of bond, it's the third one, well, your carbon has another p orbital, the pz. Now this is where things look a little bit mental. They absolutely do. Then your pz's will overlap sideways. They're beside each other. They're not spaced out like they are on my diagram. and they will overlap sideways as well. That will be your third one. Now, one thing before we move on and look at specific differences and putting them in a table is the area of overlap. If you look at the pi bond, in order for your orbitals to overlap sideways, it's like trying to get your two arms to touch like this. It's sore. When your p orbitals are overlapping sideways, they're not going to be able to overlap massively. There's only a very, very small overlap between them. Whereas when two orbitals overlap head-on, there's a lot more space. They're a lot more able to overlap head-on. So if I overlap that p orbital with that one like that, the area of overlap between the two orbitals is much bigger for a sigma bond than it is for a pi bond. Now, what I have been saying for the last 5 minutes out loud is actually loads of differences between sigma and pi bonds. And if you can remember 3 of them, you're fine. Now, one last thing. We have to be able to count them. So the easiest way to do it is actually from what I was doing there. When you have your bond type, and we have sigma and we have pi. Now, we've dealt with single bonds. Single bonds are one bond. And in terms of whether it's sigma or pi, the sigma bond will always form first. So when you have a single bond between two atoms, that has to be sigma. It can't be anything else. So single bonds will have one sigma and no pi. They don't have a second bond. They can't be pi. If you have a double bond, though, between two atoms, the sigma bond will form first. So that's 1. But now the second bond that will form is a pi bond. So a double bond has 1 of each. A triple bond between two atoms, the sigma bond will form first, so it'll have 1 of them. And then the next 2 bonds that you form to make the triple bond have to be pi. No matter whether you are dealing with a single, double, or triple, you cannot have more than 1 sigma. The multiple bonds come from pi bonds overlapping between your orbitals overlapping to give you sideways pi bonds. Now, that's important because you're going to use that to count the number of sigma and pi bonds in different molecules in a minute. Now, after all of that, I'm going to summarize what I just said on the other board, and we're going to do it as a table. Now, we're going to move over to here where I have set up a table for myself to fill in the differences between them. If the examiner asks you a comparison question where they say, compare 2 differences between sigma and pi, the number one thing that you need to do here is to do a table. Because when you are comparing 2 things, you must give information on both of them, and the table will show you if you're missing anything. If you write this out in a paragraph style answer, it can be a little bit difficult to see have you given enough information to compare the 2. Right, the very first difference between them, use the definition to help you. You have to be able to define a sigma bond and a pi bond. So now we're going to use that as a difference. A sigma bond is formed by the head-on overlap. That's not enough. Yeah, overlap of what? Atomic orbitals. It's not enough just to say head-on overlap because we're going to go, well, what overlaps? Electrons? No, it's head-on overlap of atomic orbitals. Now, for an adequate comparison, you need to tell me how the pi bond overlap is different. So a pi bond is formed by the sideways overlap, or side-on is fine, of atomic orbitals. There's one difference. Right, for one difference between the 2, that's my first 3 marks in a comparison question. But you need information on both of them. So in your table, you have to have information under sigma and you have to have information under pi. And if one of them is missing, you're going to drop 3 marks. Next, another difference, think about the order that your bonds form. Which of them is going to form first? The sigma. So a sigma bond forms first, and the pi bond forms after sigma. There's another 3 marks. 2 differences in the bag. Now, you can give me loads of other ones. You can go after whether it's single, double, or triple, or you can go after your orbitals. So I'm going to go after both, actually. So when it comes to a sigma bond, this involves all orbitals. S, P, D, and F orbitals. Now think about what orbitals can't overlap sideways. It's the S. So pi bonds does not, or pi bonding does not involve S orbitals. Or you can say that it only involves P, D, and F orbitals, not S. There's 3 marks. Another one. Sigma bonds are found in single, double, and triple bonds. Pi bonds are only found in double and triple. So not single bonds. Or you can say they are found in double and triple bonds. Now, I'm limited on space here, but there are loads of other differences. Another difference I gave you was in the area of overlap, where we said there is a greater area of overlap with a sigma bond and less area of overlap with a pi bond. That will have implications for the strength of the bond. The more overlap you have between 2 orbitals, the more difficult it's going to be to pull them away from each other to break a bond. So sigma bonds are actually stronger than a pi bond because of this bigger area of overlap between the orbitals. Now, be careful with your language there. Yes, a sigma bond is 100% stronger than a pi bond. Just be careful that you don't say that a single bond is stronger than a double bond, because it isn't. A double bond is 2 bonds, sigma and pi, whereas a single bond is only 1 sigma. You'll need more energy to break 2 bonds versus 1, but it's not double because the pi isn't as strong as the sigma. Now, there's various other ones that you can give as well. Down at the very bottom of my table in the notes, I put about the rotation around the bond. Now, I wouldn't touch that one with a 10-foot pole, but if you want to learn that one, you can. It's to do with when you start building structures in organic chemistry. When you make single bonded structures, your molecules are going to be flapping all over the place and rotating around the central bonds. However, as soon as you stick a double or a triple bond in there, there's no rotation anymore. And we're not going to get into more detail than that. Now, the next thing that we need to have a look at is to be able to count sigma and pi bonds in a molecule. So for this one, we're going to go through the worked example number 1 on page 124. It says, give the number of sigma and pi bonds in the propanone molecule shown on the right. Now, at this stage, I don't expect you to be able to draw propanone. However, once you do organic chemistry, you absolutely will be able to draw this for yourself. It's called a ketone. Prop tells you the number of carbons. Prop is 3. So there's 3 carbon atoms. 1, 2, 3. And the anone or one tells you the family, which is a ketone. Now, that doesn't mean anything to you right now, but this is what a ketone looks like. Now, carbon has to have 4 bonds, so you have to fill in all the bonds to carbon and your hydrogens. Now, a lot of you will have come across propanone before, because propanone is actually what you use to take shellac off or gel nail varnish. It's acetone. It's its proper name though. Acetone is its commercial name. Propanone is its UPAC name, and we call it propanone in chemistry. Now here, you have to count the number of sigma and pi, and that's where this table comes in handy. Anywhere where you have a single bond, that is 1 sigma and no pi. A double bond is 1 sigma and 1 pi. Don't forget the pi. And a triple bond will be 1 sigma and 2 pi. Now for this is where those of you who are stationary addicts like me, you're going to be in your element here. I want you to use a different colored highlighter for the different types of bonds. So for this, I'm going to pick one color highlighter, which are my pens, and I'm going to highlight all of the single bonds in that molecule. So I have 1, 2, 3, 4, 5, 6, 7, 8. That means I have 8 single bonds in that molecule. Therefore, I have 8 sigma from the single bonds. Now let's look for any other types of bonds. I haven't highlighted this one here. That's a double bond. Now remember, a double bond is made up of 1 sigma and 1 pi. So I'm going to highlight one of the bonds in the double bond as the sigma, and the other one is the pi bond. Now, to be honest, it doesn't matter which one you say is the sigma and which is the pi. I said the one on the left is the sigma. It doesn't matter. It actually does not matter. So that one, you have 1 double, which means you have 1 sigma plus 1 pi. Now, when you're asked to count up the total, you need to add them together. So your final answer at the end of all of this is 9 sigma for 3 marks and 1 pi for 3 marks. This is a 6-mark question where you need to give 2 numbers for 6 marks, and you'll be able to do this in about 10 seconds. It's a great question. Now, there's a couple of other questions that can come up in relation to this, so we're going to have a look at a couple more of them, and then we're going to move on. Now, I'm not going to do work example number 2. So in your notes, we're going to go through question number 5 in the practice questions. Now, for this, we have different molecules, and to be honest, you don't need to be as pedantic as I just was when I was counting that. Okay, so butane, ammonia, propene, and ethine. Let's go with butane first. So bute is 4 carbons, prop is 3. And then you fill in your hydrogens. Okay, and we count our bonds. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All of my bonds on that molecule have been highlighted. So my final answer here is 13 sigma and 0 pi for 6 marks. Now, the next one that I want to have a look at, I'm going to go down to propene, which is question C. Prop is 3 carbons, and now ENE at the end is telling you that there's a double bond in the structure. So if I draw that as 1, 2, 3, we draw the double bond there. It actually doesn't matter where I draw the double bond, but we'll see that later. Okay, now we go in and count our sigma first. So all of your single bonds, 1, 2, 3, 4, 5, 6, 7, but you're not finished. One of the bonds in that double bond is a sigma bond as well. So we count one of them, and that's going to give me a total of 8 sigma. Now you also have to count this bond as well. So the second bond in the double bond is a pi bond. So it's 8 sigma and 1 pi, 3 marks each. Now, just so that we see an example of a triple bond, we're going to have a look at ethine as well. Now, ethine is D. Eth in organic chemistry is 2 carbons. So eth is 2, prop is 3, 4 is bute. So we have 2 carbon atoms, and the YNE tells you the family. It has a triple bond. Now be careful. Go in for your sigma first. You have 1, 2, and one of the ones in the triple bond is a sigma bond. So in total, you have 3 sigma. And now for your pi, because this is a triple bond between the 2 carbons, you have to have 2 pi bonds as well. So I'm going to highlight both of those, and we write in 2 pi. Now, to practice some of the rest of the ones that are in your notes, the answers are given at the very end, so you can check your answers and see are you on the right track. But I do recommend trying them just to get you in the habit. It is a really straightforward 6 marks when it comes up in the exam. Now, one thing I will state though, is if you look at question I, this was put in to torture my lovely 6th years. So I've given you the stick structure of something called linoleic acid. You will never in a million years be asked to count the number of sigma and pi bonds in that. But that's for my 6th years that have been practicing structures in organic chemistry later on. And I want them to be able to figure out what the stick structure is. So that is way too challenging than what you'll see on the Leaving Cert, but it's there to try and catch out some of my lovely 6th years and see how they get on. If you can do up as far as question H in those counting sigma and pi bonds, you'll be absolutely fine. They're actually probably a little bit trickier than anything you will actually see in the exam. Right, that is it for sigma and pi. Now, there is another worked example that I gave at the bottom of page 124, which is counting sigma and pi bonds in that structure there. Now, that is something that you will be unlikely to see as a full structure for counting sigma and pi because of the benzene ring. It's the bit in the middle that looks like a hexagon with the circle in it. Now, it's because something weird happens with the bonding arrangement in benzene. However, I am going to draw out the full structure here and go through it with you, but just it is a little bit more advanced than what you'll see. Benzene, when it comes up, we will be discussing it a lot later on when we reach organic chemistry. Now, the structure. Give the number of sigma and pi bonds in the molecule below. That is a molecule of, I'm pretty sure it's ibuprofen. So we have a benzene ring in the middle, then we have a carbon with a CH3, carbon to hydrogen. Then we have a C double bond O up there and an OH. And then down the bottom, we have CH2, CH, and then we have CH3 and CH3. Now, before we all have a heart attack and go, oh my God, I'm never going to be able to draw that. You'll never have to. You do have to be able to draw structures in chemistry, but nothing anywhere near as difficult as that. You'll be drawing ones like the ones I had on the board previously, like propene and butane and that kind of thing. So the nice short ones. Now for this, the reason why I put this in here to challenge the 6th years in particular, 5th years, don't even worry about this, come back to it next year when you're in 6th year. For this, I'm checking, do you understand how many bonds there are when it's written like this, based on what you will see in organic chemistry later on. So here, the main problem is benzene. Now, benzene is a 6-sided or 6-membered ring with 6 carbons, where each of those sticks meet is a carbon. So I have carbon there, 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 and there. Now, typically benzene is shown with 3 double and 3 single bonds, but it actually doesn't. And if you've done organic chemistry, you know why. We've got the delocalization of electrons. Don't worry about it for now. Now, the hydrogens, it has to be 4 bonds to carbon. This carbon up here already has 4 bonds, so there's no hydrogen here. But this carbon only has 3. So we draw in a hydrogen here and one here. This carbon on the bottom does not have a hydrogen because it already has 4 bonds, but this one does. And so does this one. Now I'm going to expand the rest of the structure. So up here where I have CH3, that is carbon that is bonded to 3 hydrogens like that. And up here, the oxygen bonded to the hydrogen, there should be a bond here as well. Then we move down. Where you have your carbon with your 2 hydrogens, you have 1, 2, 1 bond to hydrogen here. And then each of these carbons has 3 hydrogens. So you have 1, 2, 3. Now this will be a lot more straightforward when you cover organic chemistry because we will be talking about this a lot more. So I'm just showing you for now so that you have an example of me going through this, but don't watch this bit until you've done organic chemistry. Now, counting up your sigma and pi, I'm just going to do it based on the representation that I have, and I'm not going to do anything here weird with the carbons and the delocalization in the middle. So I'm going to count all the sigma first, so the single bonds. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Now I'm just going to write down 29 sigma from the single bonds because if I start talking, I'm going to forget how many that was. But we're not finished. Remember, double and triple bonds also have sigma bonds in them, and I haven't counted those yet. So this double bond to the oxygen up here has 1 sigma. That's 1. There's 3 of them here. That gives me a total of 4. So it's 29 plus 4 sigma, which is 33 sigma bonds in total for 3 marks. Now for your pi bonds, you're looking for double and triple bonds. So there's 1 double bond up here. That means you have 1 pi bond there, and there's 3 in here. So 1, 2, 3. That would give us a total of 4 pi. So 33 sigma and 4 pi at the end of it. I had to double check my answer just to be on the safe side. So 3 marks each. But now that is something that I'm really checking the 6th year's understanding of organic chemistry and also expanding your structures to show all of the bonds, which is quite advanced at this level.